Welcome to hypothesis testing, a quick review. In this particular chapter, what we will be doing is setting out the basic structure and approach to hypothesis testing. So confidence intervals were a little bit more, for lack of a better term, casual. You found an interval, hey, is the value in there? Yes, no, you made determinations based on that. So very kind of, chill. Hypothesis testing, a little bit more rigorous, more set out, more structure. There'll be 6 steps to a statistical test. The steps are important. Each step has a certain important meaning attached to it. And so just a little bit more of a rigorous examination. We end up usually at the end at the same spot in both cases. It's just a certain level of formality and rigor to a hypothesis test that doesn't exist for a confidence interval. So that hypothesis test all starts off with 2 statements. As we remember this from our first stats class, we have 2 statements about the value of some unknown population parameter. Right now, we've dealt with the mean, but later on we'll deal with the variance, and then we'll deal with coefficients in a regression, and so we will expand this out quite a bit to what that HO and that HA is based around. Okay, but right now the thing we've talked about measuring is the mean, population mean. So those 2 statements, one we call HO, one we call HA, right? And in some textbooks they call them HO and H1. Old school, you'll see HO called H naught. Naught is Old British for 0, or the null hypothesis again means HO. Now, this requires us to make a decision, right? So we make a decision on those 2 statements. We either fail to reject H naught, or we can accept HA. We avoid the words except HO, okay? And that'll be for reasons that we'll get into in a second, okay? So, but essentially, we're going to either not reject H naught, or we're going to accept HA. Some of the purists will say you fail to reject H naught or you just reject H naught. Whatever. We're applied. When you've rejected H naught and all there's left is HA, you've essentially accepted HA. Okay, so what is this H naught, HA stuff? I mean, we've got this flying around. What do we mean? So HO typically represents sort of a status quo. So if you think of a scientific hypothesis, HO would represent the traditional way we've always done it, the way we're doing it now, that kind of thing, right? Sometimes you see the word claim, that means HO. But essentially, HO is just the status quo or the traditional way of doing it, or some sort of claim that, hey, we've always thought it was this way. Now, show me wrong, the kind of thing. This hypothesis is the default, so it stands unless we can show that it is no longer valid. Okay, so if we can't dispute this, we just leave it as is. We don't really accept it. We just say nothing to suggest this isn't the best way to do it. Right? This other way isn't better. It's kind of like the way we're looking at it, right? And that other way is the alternative hypothesis, or HA. So we have to show that HA is better in some dimension, right? Better, I'm putting under quotation marks, but in order to invalidate HO. Okay. So this hypothesis is accepted only if the data provides convincing evidence of its truth, and it has to do that. And in some ways, we have a couple of different ways that we can look at things. Right. A lot of times, one of the nice examples it's easy is HO just means that a person is not guilty. HA, guilty, right? And in our criminal justice system, you have to establish, beyond a reasonable doubt, which is just another way of saying alpha, beyond a reasonable alpha, that someone is guilty. if we can't show that they're guilty, we just say, okay, you're not guilty then. But we've not said you're innocent. To say you're innocent would mean accepting HO. And, in hypothesis testing, as in the justice system, we don't accept HO. We just say, hey, did you prove HA? Guilty? Yes. Okay, they're guilty. No, they're not guilty. And we just go about, you're presumed to be not guilty unless you're shown to be guilty. Okay? So we have a presumption of innocence when you're not guilty, but we haven't proven innocence. Okay? So that's kind of like probably the most easy to visualize distinction between HO and HA. Now there's this slide. What the nature of errors. Type 1 error and type 2 error. And I know right now your eyes are glazing. You start to snore a little bit and you're going, oh crap, man, I remember this damn table from the first stats. Oh, so theoretical, so much BS, so I don't care, so little caring right now, so don't give a don't give a hoot. But this is extremely important, and it actually took me quite a while to actually appreciate it. I think I've taken a lot more stats classes than you have, and I've seen this table a lot more than you have. I guarantee it. And I think for the first 4 times I saw this thing come up in class, I went, oh crap, yeah, who cares, right? Flip, don't care. But this friction, this balancing between type 1 and type 2 error is very, very important. And so let's just talk about a little bit about what that type 1 error is. Okay. Now, it is the type 1 error. It's a probability. So it's a probability that you reject H naught given that H naught is true. Right? Type 1 error right here. Reject the null given that the null is true. Okay, so we reject H naught. We shouldn't have rejected H naught. We make that mistake. Type 2 error, if I can learn how to write again, and I'll just state it a little bit different, just so that we have the same cadence here. Reject HA given that HA is true. And I know in the table it's represented in more of a theoretical statsy kind of way. Do not reject the null when the null is false, which is like saying that HA is true. Okay. A lot of times in the more theoretical way of looking at hypothesis testing, everything is centered around rejection or not rejection of the null, and HA is almost like an afterthought. We're in an applied field. HA is not an afterthought to us, so we're going to just bring it straight in and be maybe a little bit more pragmatic in how we're reviewing our statistics. Okay, so we have this balancing act in between type 1 and type 2 error, right? If you minimize the probability that you reject H naught given that H naught is true, you're increasing your chances of rejecting H naught A when HA is true. Right? So you're balancing that out. If you want to make it very, very unlikely for you to falsely reject H naught, you are going to make it a little bit more likely that you're going to falsely reject HA. Right? There is a trade-off here. Right? It's a real world stuff. It's not a trade-off. Let's see how real world it can be here. Okay. So let's go with HO. We have a vaccine, very topical. Vaccine is ineffective, right? And we start off, and that's just not controversial. That's just the way we approach the scientific hypothesis, is that we assume that a particular vaccine does not work unless we can establish that the vaccine is effective. Right? We don't assume that it works. We test it. That's why they run the tests, and that's why the Moderna ran the tests, and that's why Pfizer's run the tests, and that's why AstraZeneca's run the tests, and so on, right? As we're trying to see if the vaccine is effective. So, what's the type 1 and type 2 error here? Right? Type 1 error. Well, that's the probability. We reject H naught. So what's that mean? That means the vaccine, we say the vaccine is effective given, right, the vaccine is not ineffective. The vaccine, is ineffective. Right? Well, saying it's effective when it's not, that's a serious error, right? It's a concerning error. Type 2 error, what would that be? That would be the probability that we reject HA. So we say that the vaccine doesn't work, right? Vaccine is ineffective when the vaccine is actually effective. Okay, tough decisions, right? We're saying that the vaccine is ineffective when it actually is effective. Right? And so now we're balancing off the two types of errors. We certainly don't want to say vaccine is ineffective when it is effective. My gosh, I mean, then that could delay us getting the vaccine out to folks. But on the other hand, we don't really want to say the vaccine is effective when it's not either, because it gives people a kind of a false sense of security. But those are the two errors that we have to balance out. And that's not a stats issue, right? We phrased it in a stats manner so that we can sort of isolate and see and visualize and comprehend the problem. Now, do we prefer smaller or higher type 1 error? Because type 1 error is the one we have more control over. Well, that's a public policy, that's a public health issue, right? Mostly a public policy issue as to how we weigh that up. We can frame it statsy-wise. The actual decision as to how big or small to make that type 1 error, that goes off to other folks, right? But you can kind of see how just looking at things in this type 1, type 2 error framework really gets you a sense for the weightiness of the problem and the sort of the two aspects of the problem that we need to consider in this case and how important it is, right? So looking at the world through the frame of this, type 1, type 2 error is not as theoretical as most textbooks and a lot of courses make it out to be. So very powerful stuff there. Just so you know, I think it's in midterm 2. I typically ask a question where okay, in this problem, frame this question in terms of type 1 error, type 2 error, and now weigh it. Do you make that alpha bigger or smaller? Okay, alpha centers around the type 1 error. It's really hard to get a handle, a strong numerical handle on type 2 error, because it requires us to make certain assumptions on the nature of HA, and we simply don't know what the nature of HA is. All our tests are all centered around the distribution that HO follows, and so we have a little bit more of a theoretical handle on HO than we do on HA, so we tend to focus more on controlling type 1 error. But as you can kind of see, as you make that type 1 error smaller, or the tolerance for type 1 error smaller, type 2 error does increase, and vice versa. Okay, so maybe we can't get an exact measurement for how type 2 error is impacted, but we do know it goes up when type 1 error goes down. Okay, so powerful stuff there. Another important player in all this is the good old p-value. Okay, so we calculated the p-value, and we did this in our first statistics. Now, I'll give you my two flavors of it. First, the statsy flavor of it. The probability, the p-value is the probability that the test could be that extreme if the null hypothesis is true. At which point everyone goes, what? Huh? Yeah, really? What the hell does that mean? And then the statsy people go, "Ooh, that's complete. That's good." It's also kind of useless too, right? So it's that's technically true. Awesome, cool. Really hard to get any practical kind of feel for it. The more practical feel for it is it's like your observed level of significance. So alpha, which we'll see in a moment, is sort of our tolerance level for type 1 error. This is the p-value gives us the sense for what type 1 error would be, or observed level of significance, another word, if, big conditional, if we were to reject H0. If. We don't maybe that we don't reject H0, but if we were to reject H0, the p-value tells us what's our probability of committing a type 1 error. A little bit more intuitive that way, okay? At the end of it all, we're going to compare that p-value to alpha, decide whether to reject or not reject H naught. Okay, so we used it in our decision making. The nice thing about the p-value versus critical value, finding critical values and comparing things to a critical value and so on, which is sort of the 1800s old school pre-computer methodology, is that with smaller p-value we have, the stronger the evidence against H naught is. Okay, so maybe we got kind of a high-ish p-value, whatever high-ish may be. We go, okay, we'll reject H naught, but I'm really nervous about it. Versus a very small, low p-value and go, yeah, H naught, get the heck out of here. Beat it, get out. Don't want to see you. Don't let the door hit you in the butt on the way out. Okay? We know HO, got full confidence in saying load of crap. Okay? So that p-value gives us maybe a certain level of comfort as to, how much vigor and we can reject H naught. Okay. Now, the testing formats, all nice and easy. Just as an aside before we get too far out, when you see a mu with a little zero, mu naught, that just means that's a placeholder for a particular value. Okay? Never write mu naught on any hypothesis test. Ever. Nothing says you don't know what's going on than to write mu naught in a hypothesis test. Right? Nothing screams out to me, oh my gosh, I did not study, more than seeing somebody write mu naught in their hypothesis, because it means you looked at the slides and had no idea what the heck was going on. Very disconcerting. Okay, so mu naught, a placeholder for a specific value. That specific value will be mentioned in the question. Okay, so HO, you'll notice that there's a theme to HO, always has an equality sign in it, right? Mu is equal to some value. Mu is greater than or equal to some value. Mu is less than or equal to some value. Always an equality sign in HO. Never ever an equality sign in HA. Right? HA is mu is not some value. Mu is less than some value, or mu is greater than some value, but never ever an equality sign. So that structure, very important. Easy to a lot of people get them mixed up, get a little dyslexic and stuff like that. Just be very careful to give it a second look or a double check to make sure you're not making simple mistakes like that. Okay. So we have our HO, we have our HA, we have an alpha, we've got that type 1, type 2 error balancing out in our heads, a lot of stuff going on. We've got this p-value, and the p-value depends on some test statistic. What the heck test statistic does it depend on? Well, we got our good friends back, the Z and the T. And how do I know whether it's a Z or a T? Centered around that one question, and that one question only. Is the population standard deviation known? If it is, you're calculating a Z-stat. If in the more likely case it is not known, you're calculating a T-stat. Same exact way we looked at a confidence interval. No doggone difference. Right? We have our Z score calculation, x bar minus a specific value for mu, right? Divided by sigma squared n, which is just the standard deviation for the mean. Cool, right? Saw that before, worked with that a lot. T, same structure, right? Only difference is it'll follow a T distribution, Z will follow a Z distribution, or normal distribution. Okay, so very, very similar formulas, easy peasy. Okay, so there's our test statistic, which we will use to find the p-value. And we've got a couple of ways that we look at those p-values depending on the HA. Right? So we saw three flavors to HA. We saw HA is maybe not equal to some value. That means that the value could be greater or less than, right tail or left tail. Right? And so the p-value is the summation of those two areas. Okay? So typically, because it's a symmetric distribution, both the t and the z are both symmetric, we just have to calculate the area in one tail, times it by 2, and we've got the area in the two tails. So that part's not too hard, right? Just two tails. So if it's a two-tailed test, that's where the word two-tailed comes in. Right? So if we have a two-tailed test, that means we don't care if mu is greater than this value. We don't care if it's less than this value. We just want to know if it's one or the other. Two tails. I don't care if it's in the right-hand tail. Don't care if it's in the left-hand tail. Is it in a tail? Right? And I'm looking at two tails when I make this determination. Versus the other choices where, hey, I only care if mu is less than the specific value. Do I care if it's greater than? No, I don't care. Just is it less than this value? Right? So I'm only looking in the left-hand tail. Hence, a one-tail test. And then the last HA here is mu is greater than some value, which means I only care if it's in the right-hand tail. I don't care about anything, whether it's less than or if it's equal to. Not so concerned. Just, hey, is it in the right-hand tail? Yes or no. It's a one-tail test. And I'm just concerned about the right-hand tail or the greater than area. Okay, so one-tailed, two-tailed. And that's what we get when we're doing up our little pictures and stuff. Okay, that Z could easily be switched out for a T. It's same conceptually, it's exactly the same. So let's wrap this all up, but with and bring it all together and finish up this particular segment. Is what's our structure? And these are the two most important slides in this whole section. First step, we have to state HO and HA. We've got to know what is the problem that we're examining. What is it? Right? So we state our HO, we state our HA. Most of the time what we see in the question is HA, and HO is just the opposite. Most of the time, but not all the time. And we'll see the differences in the future. Okay? Step 2, we're going to state alpha, the level of significance. Now, from a practical matter, in an exam situation, I will give you alpha, but there is an awful lot of thinking that goes into what's the proper alpha, right? We just saw our balancing between type 1, type 2 error, right? Weighing it in the vaccine case. How extremely important that is and how consequential it is. And so often in an academic environment, alpha is whatever alpha is, right? And so often we assume alpha is 0.05. Why the heck do we assume it's 0.05? What's magical about 0.05? Absolutely freaking nothing, right? Irving Fisher, who first came up with hypothesis testing, or first discovered hypothesis testing, just picked it randomly. Said, that seems like a pretty good, decent value, but hey, don't put too much weight into this value because I'm just sort of winging it, just pulling it out of my backside here and just throwing a value out there and going with it. And then everybody just ignored the fact that he said, well, don't be careful using this 0.05 as something magical, and then we all use it as something magical. Right? Alpha is 5% or 0.05 has become a magical number. It was never intended that way. Right? It was just basically a pull it out of his backside kind of number. Right? So we got to keep the weighty issues of what it means when we start talking about this type 1, type 2 error stuff. Right? So for the most part, it won't be as much brain sweat as we just did, but understand we should think about it far more than we do. Next step, compute the test statistic, right? Whether it's a Z, whether it's a T, or whether it's some of the future test statistics that we'll see later on. And report the degrees of freedom if that's applicable. A T statistic without a degrees of freedom, it's a two-legged table. Right? It makes no sense. We have no context to put it in, right? So if you're reporting a T statistic, or if you're reporting any test statistic that has a degrees of freedom, you must put the degrees of freedom as step 3. Step 4, use that test statistic to compute the p-value. And then the big rule, step 5. This big important rule that you need to know, love, and embrace. Put it as a sticky by your computer, whatever. Step 5, make the decision. We're making decisions, right? We are in an applied field after all, and decisions are what we do. If that p-value is less than alpha, the test is significant. Reject H naught, accept HA with an error probability of alpha. Okay, so we got to get some statistic boilerplate language in there, and just make sure that's all tidied up. Okay? But essentially what's that saying is my risk of committing type 1 error, right? The probability I actually commit type 1 error if I reject H0, which is the p-value, which we saw before, is less than my threshold, which is alpha. Alpha sets my maximum upper bound for committing a type 1 error. So if my risk of actually committing a type 1 error is less than my tolerance for that risk, I'm good. Reject H0, feel good about it. If that risk of committing a type 1 error is too high, right, i.e. is the p-value too high, and by too high we mean it's greater than alpha. Again, alpha being my risk tolerance, my risk limit for committing a type 1 error. If it's too high, if my probability of committing a type 1 error is higher than the maximum I've set, I don't have enough evidence to reject H0, so I'm not going to reject H0. Again, with the error probability of alpha, right? Because perhaps a slightly different choice for alpha, we might make a different decision. Very important rule. And step 6, probably the most important step in all of this, is state your conclusion in regular language. Keep the stat speak out of there, and that's harder than you think. Just something, take the most non-statistical person that you know, and if you ran step 6 past them, would they understand what the heck it is that you just concluded? Right? Many times the whole reason why you've been hired to run the stats on this is because somebody else doesn't know how to do it, doesn't care to do it, but they do want to know what the heck is your conclusion, and they want to be understandable. Right? Communication is very important to us in a business program. So being able to communicate what it is that you are actually recommending is very important. All right, let's move on to step 2. With that, step 2 will be do some examples. Anyway, see you soon.